going to be talking about a particular approach to the Riemann hypothesis that I had been working on for a few years, over the last 2 or 3 years. And so afterwards, I began working with it with 2 of my PhD students. So I'd like to share with you some of that work, some of which is published, some of which is in the form of preprints, and basically to introduce this particular approach to the Riemann hypothesis. Let's start. Okay, so first of all, just to introduce the Riemann hypothesis, of course, almost all of you will know what the Riemann hypothesis is, but perhaps for some students that are here, the Riemann hypothesis postulates that all non-trivial zeros of the zeta function. So the zeta function is defined as a Dirichlet series on the right half plane. This series, of course, converges only when the real part of S, the variable S, is greater than 1. So it converges on the complex plane to the right of this line. But of course, we know that it has a meromorphic continuation, an analytic continuation to the whole of the complex plane with a pole at the point 1. So the Riemann hypothesis basically postulates that the zeros of this analytic continuation within this critical strip should all lie on the critical line. That's the Riemann hypothesis. Okay. So of course, Riemann hypothesis is a very old, probably the most significant open problem in mathematics. So in 1950, Nyman, a student of Burling, worked on a particular reformulation of the Riemann hypothesis in terms of Hilbert spaces. This is probably the first such reformulation. And so what he proved was that suppose lambda is any real number between 0 and 1, and let rho lambda be defined as such. So these brackets are the fractional part of lambda divided by x minus lambda multiplied by the fractional part of 1 over x. Okay, so these are functions. These are real functions. In fact, I believe they're positive also. So what was the Nyman and Burling theorem? It states the following, the following 2 statements are equivalent. The Riemann hypothesis is equivalent to the characteristic function of the interval 0, 1. So basically the constant 1 belongs to the closure of the span of all of these functions in L2 of 0, 1. So this is the Nyman-Burling criterion for the Riemann hypothesis, about 70 years old now. So basically, the Riemann hypothesis is recast as a as a problem of approximation in L2. So it has absolutely no number theoretic content. So of course, this spawned a lot of research. A lot of work was done after this, because of course, then you could use Hilbert space methods, etc. So I will try to give a sketch of one part of the proof of this, because I believe that looking at this result on its own doesn't really reveal much of the connection, because this seems to be, a functional analysis, a basic problem about approximation, that, a function belongs to the closure of the span of certain functions. And the Riemann hypothesis, of course, is a problem in number theory, or complex analysis rather. So I'm going to give one direction of the proof, which is the easier, but it also reveals why this is the case, why this result holds. So first of all, the Fourier-Mellin transform. So this is the Fourier-Mellin transform. It's basically a variant of the Fourier transform. Is an isometric isomorphism from the space L2 onto the Hardy space of the half plane. So the Hardy space of the half plane C1/2 basically implies all the holomorphic functions on the half plane with real part greater than 1/2. Obviously, the 1/2 is not a coincidence, because as we saw, we're interested in. So another thing I should mention is that from basic Riemann zeta function theory, we know that the zeros of the zeta function, if they exist, they are distributed symmetrically along this critical line. So if there's a 0 on the right side of this plane, in this critical strip, the right side of the critical line, then there should be one on the left side as well. So they're distributed symmetrically. So what this means is that we don't really need to consider the whole critical strip, we can only consider the part greater than 1 over 2. So, sorry. So that's why this 1 over 2 is important. So these are holomorphic functions in the Hardy space defined on C1 over 2 to the right of 1 over 2. So this is an isometric isomorphism. So of course, functions here are holomorphic. They also have non-tangential boundary limits, meaning that if you consider the limit of each function here as the real part converges to the boundary, so it defines a function in the L2 space on the critical line. L2 space on the critical line is basically a copy of L2 on the real line. Okay, and also this is a reproducing kernel Hilbert space. So we'll talk about reproducing kernel Hilbert spaces. So what is the idea of the proof of the result? So the first observation is that from a simple computation, if you take the Fourier-Mellin transform of the functions rho lambda, just to remind you, these are the rho lambda. If you take the Fourier-Mellin transform of these functions, what you get is this. So you notice that the Riemann zeta function appears here. And this factor, of course, lambda is a constant in this case. So when s is equal to 1, this factor is 0. So zeta function has a pole at the point 1. So the pole and the 0 cancel. So this defines a holomorphic function in the plane, in the right half plane. So this is essentially the relation of the approximation problem with the zeta function. Okay. So in other words, what this means is that if the Riemann hypothesis is false, what does that mean if the Riemann hypothesis is false? It means that there is a 0 here, that it must have some 0 outside the critical line, but within the critical strip. But if that's the case, if that is the case for some w, then that means all of these functions, which are the images of the rho lambda, must have a 0 also. In other words, the span closure of these functions must consist only of functions that vanish at this point. So that means, in other words, of course, this is a consequence of the fact that the Hardy space is a reproducing kernel Hilbert space, which in other words implies that evaluations are bounded linear functionals. So the fact that these functions are 0 at this omega, supposed 0 of the zeta function, will extend to the whole of the span. Okay, so now let's see what happens when we take the Mellin transform of the characteristic function from the Nyman-Burling theorem. We get the function 1 over s, but notice the function 1 over s doesn't have any zeros. So in other words, what we have shown is that this cannot, 1 over s cannot belong to the span closure of these f lambda, because all the functions here must vanish at the point w. So in other words, 1 over s does not belong here. Because we use the Mellin transform, so if we go back via the isometric isomorphism, what this therefore proves is, what we've essentially proved is, that if the characteristic functions belongs to the span closure of the rho lambda, this must imply the Riemann hypothesis. Because above we proved the contrapositive. We prove if the Riemann hypothesis is not true, then the characteristic function should not belong to this. So this is the easy part of the proof. The other part is a little bit more technical, obviously, and much longer, but I believe that this part is more interesting also because you have a sufficient condition for the Riemann hypothesis. Okay, so that was from the 1950s. So more recently, Duarte in 2003 proved a remarkable strengthening of the Nyman-Burling criterion by showing that actually we don't need to consider any lambda in the above criterion. For example, here the span is taken over all lambda, so you have an uncountable family of functions. He proved that actually this is not necessary. We can just choose a countable family. In other words, just a sequence. If we take lambda is equal to 1 over k. So he proved that the Riemann hypothesis is equivalent to the characteristic function of the interval 0, 1 belonging to the closure of the span. So this is quite a significant strengthening. One of the properties of these functions is, if you restrict lambda to 1 over k, is that they are actually almost everywhere constant on the intervals. They're constant on these intervals. So I've actually, just to illustrate this, I've actually drawn a graph, plotted a graph of one of the examples of these functions. Can you see GeoAlgebra? Aparece ou não? GeoGebra.
Sim, okay.
Aparece. Ok, perfeito. Obrigado. So I've given here an example of that function choosing lambda equals 1 over, so k is equal to 10. So lambda is equal to 1 over 10. So when you plot this function, you can clearly see here that the function, the graph of the function are constants on certain intervals. They're almost everywhere constant, basically. If you go closer, you can see there's small intervals close to the origin as well. And of course, if you change the values, so notice there's 10 rows, 1, 2, 3. This is not a coincidence. If you change here from 10 to 5, for example, so lambda is equal to 1 over 5, you should get 5 different lines. So basically, once you increase, if you go to 1 over 100, 1 over billion, so you get basically functions which are almost everywhere constant, something like step functions or simple functions. Of course, a consequence of this is that the span cannot be dense in the L2 space. So using this observation, the fact that these functions on certain intervals, countably many intervals, have a constant value, in 2004, Balazard and Saiz considered a further reformulation of Bayes-Duarte by putting the values, by considering it as a weighted L2 space, basically a weighted sequence space. That is because of this observation that those functions are almost everywhere constant. So basically the idea was to take the values and put them as the coordinates of sequences. So what they formulated was the following. There's an equivalent version of Bayes-Duarte in the weighted L2 space with the following inner product. It's weighted because we have a weight 1 over n into n plus 1. So in this reformulation, you can choose, instead of functions, you can choose sequences Rk, which are periodic. So this is even simpler in appearance, at least. It's a very simpler reformulation. So Rk is basically a k periodic sequence from 1, 2, 3 until k minus 1, and then it repeats. So then the Riemann hypothesis becomes equivalent to the constant sequence 1 belonging to the closure of the span of these periodic sequences. So this looks like a very simple criterion that whether any sequence or the sequence, a constant sequence, can be generated by linear combinations of periodic sequences. But of course, the underlying Hilbert space isn't so simple. It's a weighted L2 space. So now I'm going to start from here describing my idea of trying to use this reformulation and moving it to the Hardy space, of course. So the Hardy Hilbert space, which I'll introduce now. So the Hardy space H2 is a Hilbert space of holomorphic functions on the open unit disk, basically consisting of power series whose coefficients are L2 sequences. So it naturally inherits an inner product from the Hardy space as follows. Okay, so it's basically a copy of the L2 space. So another property of the Hardy space is that it is a natural subspace of L2 on the unit circle. So T represents the unit circle, the boundary of the unit disk, because functions of the Hardy space are holomorphic in the unit disk. So basically, via this natural association of power series with Fourier series, we get a natural isomorphic embedding of the Hardy space into the L2 space of the unit circle. And of course, Hardy spaces are reproducing kernel Hilbert spaces, which is very important, which basically means that for each point alpha in the disk, there exist functions reproducing kernels defined like this for each alpha, which reproduce the space in the following sense, that if you take any function in the Hardy space, then evaluation of that function at a fixed point alpha is basically taking the inner product of f with this kernel. So it's a reproducing kernel. So evaluations are bounded linear functions, essentially. The reason why I mention this is because this property is what differentiates this from the L2 space, for example, or sequence spaces. The L2 space is a function space, but it's not a reproducing kernel Hilbert space. Okay. Okay, so why an H2, a Hardy space version of, why an H2 version of the Bayes-Duarte criterion? Well, first of all, H2 is the prototypical example of a reproducing kernel Hilbert space of holomorphic functions. It's a very classical space. It has a lot of a very rich theory in terms of factorization, interpolation, zero sets, Carlson measures, a rich function theory, basically. And also the concrete operator theory is quite deep in the Hardy space. So there's a vast amount of literature. But finally, as we will see now, it also has a very rich and a large theory in terms of Hardy subspaces. So subspaces of the Hardy spaces which have their own topologies. This will be very important because if you look at, okay, so I have not reformulated it yet. I'll talk about it soon. Because understanding subspaces of the Hardy space will be very important to our approach to the Riemann hypothesis. So the basic strategy is the following. First of all, the L2 space where the Duarte criterion lies is to be transferred to a particular weighted Bergman space. So this is another space of holomorphic functions whose inner product is very similar in form to the weighted L2 space. In fact, it's identical. So we can naturally move any periodic sequence, for example, from our characterization and put the coefficients as the coefficients of a power series. So this is the weighted Bergman space, but we want to move to the Hardy space. So for this, fortunately, we have in the literature a very convenient isometric isomorphism from the Hardy space onto this particular weighted Bergman space. And it has a very function theoretic form. So basically, it's 1 minus z, the polynomial, multiplied by the function g, its derivative divided by 1 over z. So this is a unitary map from H2 onto the weighted Bergman space. So in other words, to get our characterization in the Hardy space, we need to move from the sequence space to the weighted Bergman space and then take the inverse of T to go from A to H2. So when we do all of this, what do we get in the end? It turns out, of course, there's a lot of subtle computations involved using some more involved Hardy space theory using local Dirichlet spaces. But the idea is that in the end, the periodic sequences 1, 2 until k minus 1, they are mapped onto this holomorphic function 1 over 1 minus z, the logarithm of this polynomial divided by k. And what happens to the constant sequence? It becomes the constant function 1. So therefore, we can finally reformulate the Hardy space version of the Duarte criterion, which is basically the starting point of our work. So the Duarte criterion in the Hardy space. So the Riemann hypothesis holds if and only if the constant 1 belongs to the closure of the span of these functions, these holomorphic functions in H2. Okay, so this is the starting point, of course. This is just a restatement of Duarte in the Hardy space. Okay, so the natural question then is, one has to ask is that these spaces, of course, are subspaces of the Hardy space, but do they have some other interesting properties? Because the reason why we wanted to work in the Hardy space is to take advantage of the rich theory, operator theory, concrete operators that exist in the Hardy spaces or exist in the context of functions, but don't exist in sequence spaces, for example, or even in the L2 spaces of almost everywhere defined functions. So for this, let me introduce some general notation. So let S be a semigroup of bounded linear operators on a complex Hilbert space. So it's a semigroup of bounded linear operators. We will say that a vector X is cyclic for the semigroup if the span of Snx, the closure of the span, is the whole space. In other words, the closure of the orbit of X under the semigroup is the whole space. The orbit of X generates the whole space under the semigroup. We call it cyclic. And of course, a closed subspace is invariant under the semigroup if it is an invariant subspace under each one of the operators in the semigroup. So combining these two, it follows that if X is a cyclic vector, which is contained in an invariant subspace under the semigroup S, it follows immediately then that this invariant subspace must be the whole space H. Why? Because H is invariant under the semigroup, but at the same time, X is a cyclic vector. So it will expand and generate the whole space. So it's a simple observation, which is a crucial step in the proofs. So now let's apply this to the concrete semigroup that we have in mind. These are weighted composition operators. So if C belongs to H infinity, which is bounded holomorphic functions on the disk, and phi is a holomorphic self-map of the disk onto the disk, then a weighted composition operator is defined as follows. So basically, W of F is C multiplied by F composed with phi. So a weighted composition operator is the combination of the two most basic operators or operations that you can do between holomorphic functions, multiplication and composition. And that's one of the reasons, motivations for coming to the Hardy space as well, because these operators don't have simple representations in sequence spaces, for example. It's not very easy to define what a composition would look like in terms of the corresponding sequences in L2. It would be very complicated. But in the context of Hardy spaces, of function spaces in general, this is very natural. And of course, there's a vast literature on weighted composition operators. So this is the general definition. So the particular weighted composition semigroup that we are interested in is the following. So it is defined as follows. Wn is equal to this polynomial 1 plus z plus z raised to the power n minus 1 multiplied by f composed with z raised to the power n. You can write this also like this. So what is so special about this weighted composition semigroup? Well, what is special is that this subspace, the span closure of HK, turns out to be an invariant subspace for the semigroup. So that provides us then with a powerful tool to study that subspace. So in particular, each one of these is a bounded operator and it is a multiplicative semigroup. It has this multiplicative property. In other words, this means that they're determined by the primes because of the multiplicity. So hence, this semigroup is a multiplicative semigroup. And another interesting property it has is that the image of each of the HK, remember HK are the functions here whose span we are interested in, the closure of the span. If it contains one, then we have the Riemann hypothesis, of course. It turns out that the image of HK is actually HNK minus HN. So it's a linear combination of the HK. And this is actually how one proves that if we let n be the span of the HK, then n is an invariant subspace under each Wn. And of course, we should recall that the Riemann hypothesis is equivalent to the statement that the constant one belongs to the closure of n. So we've proved that n and n closure are invariant subspaces for Wn. So then the next question is, what is so special about the function n, the constant function n? Remember, the function n is a direct consequence of the characteristic function in the Nyman-Burling criterion from 1950. But what is so special about the constant function 1? Does it have any relationship with this weighted composition semigroup? It does. It turns out that this is a cyclic vector. This is a cyclic vector for this weighted composition semigroup. This is not hard to see. So remember, cyclicity means that the orbit of one should be dense. Indeed, if you take the images of one, you get these polynomials. It's not hard to see. If you take f is equal to 1, you'll just get this polynomial. And these polynomials, the span is actually dense in the whole space. So this proves that 1 is a cyclic vector. So this then allows us to further generalize, and you could say strengthen or generalize the Duarte criterion as follows. So the Riemann hypothesis is equivalent to the fact that the closure of n contains a cyclic vector for W. And equivalently, as we mentioned here, that if a subspace contains a cyclic vector, then it must be the whole space. So in other words, we actually have completeness. This means that the closure of n is the whole space, or the span of HK is dense. So the approximation problem is equivalent to a completeness problem. So that means what is special about 1 was that if 1 belongs to the closure of n, actually the closure of n contains the whole space. Hence, whether or not n closure is a proper invariant subspace for the semigroup is equivalent to the Riemann hypothesis. So in other words, the Riemann hypothesis becomes a problem about or could be attacked by trying to understand the invariant subspace lattice of this semigroup of operators. So it becomes a problem in operator theory. Okay, so now we consider a somewhat easier. So now we consider an analogous problem to the previous completeness problem, which is somewhat similar, but not so much similar. Just to see how one could begin to approach this problem of attacking the Riemann hypothesis. Because until now, we've been looking at different equivalent versions or reframing the Riemann hypothesis. But now let's try to get closer to it using these various reformulations that we have, using function theory, using spectral theory, using the theory of Hardy spaces, which was the original goal. So the first thing we notice is that if we let S be the shift operator on H2, what is the shift? It is multiplying by the independent variable Z. If you multiply the function by Z, it is the shift, the most important operator perhaps in operator theory, the most simplest operator. It appears in all areas, many areas of mathematics. Yes, it appears in dynamical systems, in ergodic theory. So it turns out that identity minus S has dense range in H2. So why is this important? This is important because if the Riemann hypothesis holds, remember, we showed that if the Riemann hypothesis holds, then N should be dense in H2. So if I minus S has dense range, then if we apply I minus S to N, then it should also have dense closure, or it should be dense in H2. So why am I applying I minus S? The idea is I minus S is basically the polynomial 1 minus Z. So if you go back to the original functions, you have a factor 1 over 1 minus Z. So the idea is if we remove this factor, what happens to the rest? Is it still complete in the Hardy space? Just to have an idea of how things work. So it turns out, so 1 minus S of HK is exactly the logarithmic part of those functions. So it turns out that actually these functions, their span is dense in H2, independently of the Riemann hypothesis. So this is something we were able to prove. And this is quite an important result in terms of its applications elsewhere. So again, we're trying to prove, so the Riemann hypothesis is equivalent to N being dense in H2. What we prove here is that identity minus S into N is dense in H2. This is quite interesting also because, of course, first of all, I should mention that I minus S is not invertible, because if it were invertible, this would immediately imply the Riemann hypothesis, and then I wouldn't be here, right? Brincando. This is a densely, so the inverse exists formally, but it isn't a bounded operator. It is an unbounded, densely defined operator. Of course, this is clear from this fact that I minus S has dense range. So the inverse isn't defined as a bounded operator. But it is still very curious that if under the image it is dense, what happens under the pre-image? Why shouldn't N be dense? So here I have a short sketch of the proof. So the main idea here is, I don't think I will go through the sketch of the proof. The main observation here is that this is the first part in the work where number theory plays a role in the form of the prime number theorem. And that is that we have to prove a certain approximation in which the Mobius function appears. And in this proof, we must use different forms of, or different properties of the divisor functions and certain statements which are equivalent to the prime number theorem. So in other words, this result is in some sense related to the prime number theorem, just like the strong version is related or equivalent to the Riemann hypothesis. So even though you can't really see number theory involved, but underneath, some number theory is happening in the background. So now let's come back to that question about what can we do about the inverse of I minus S? We know it's not invertible. In the Hardy space, it's not invertible. That doesn't mean it doesn't have an inverse, or formally doesn't have an inverse. Because notice that I minus S F is just multiplying by 1 minus Z. So formally, the inverse should be multiplying by 1 over 1 minus Z. That's formally what the inverse should be. Now, this operator, of course, as I mentioned, is unbounded on H2. And this is easy to see also, because if you apply it to the constant 1, you get 1 over 1 minus z, which has the geometric series. And of course, the coefficients are just 1, and so the coefficients are not in L2. So it can't be in the Hardy space. So this is a simple example of a holomorphic function, which is not in the Hardy space. So of course, this proves that this isn't a bounded operator. Now, even though this is unbounded, that doesn't mean it can't be bounded on a larger space with a weaker topology. For example, if we consider the space of holomorphic functions on the unit disk with respect to a weaker topology than the Hardy space, meaning the topology of uniform convergence on compact sets, local uniform or compact open topology, then in this space, this function is bounded, it is continuous. Using this fact and the fact that the Hardy space topology is stronger, meaning convergence in Hardy space implies convergence locally uniformly, the previous result has the following, this result, that means we can invert this in a weaker topology. So what this implies is that a weak form of the Riemann hypothesis holds, that N is dense in the Hardy space with the topology of uniform convergence. So that means if we weaken the topology, we get a statement which independent of the Riemann hypothesis, which supports the Riemann hypothesis. This is what we would expect to be true if the Riemann hypothesis is true. So we can consider it Riemann hypothesis in the weak topology. So now let's go a little bit further. So the next approach we can do is, we've seen various approaches. We can try to prove whether, so we've seen at least 3 approaches. We've seen the invariant subspace approach. We could show that the constant 1 belongs to the closure of the span of the HK, or we could show that the span of HK is complete. These all have different approaches, presenting different methods of attacking the Riemann hypothesis. But another approach that one could use is that if, for example, if the span of HK is dense in H2, then the orthogonal complement should be trivial. The orthogonal complement of HK should be trivial. So in other words, the Riemann hypothesis is equivalent to the orthogonal complement of N, or these functions, being trivial. This is another approach which presents different methods. So for this, I would like to introduce some different spaces in order to make use of this approach. So generalized Dirichlet spaces are basically subspaces of the Hardy space, defined as follows. If mu is a finite positive Borel measure on the circle and p mu is its Poisson integral, then the generalized Dirichlet space consists of Hardy space functions that satisfy this condition. This is a particular Dirichlet integral. Now these spaces are Hilbert spaces with their own norm. They don't inherit the norm from the Hardy space. In particular, when mu is chosen to be the Dirac measure at a point on the circle, for example, zeta is a point on the boundary of the unit disk, so it's on the circle, we call it the local Dirichlet space. And in this particular case, the Dirichlet integral becomes of this form, something much simpler. And this is an area measure on the unit disk. So these spaces are what we would like to focus on. So they actually have a much simpler reformulation also, these local Dirichlet spaces. A function f belongs to the local Dirichlet space at zeta on the circle at this point if it can be represented in this simple form. F of z is equal to z minus zeta multiplied by g, which is any function in the Hardy space, plus a. So this is a much simpler representation. So one immediate observation is that these functions, when z converges to zeta, will converge to a. So in other words, the radial boundary limits of f always exist at the function zeta. In fact, they are bounded linear functionals. So the process of taking a radial limit is a bounded linear functional in the local Dirichlet space, but only at the point zeta. That is why zeta is special. These are proper but dense subspaces of H2, but are not closed in H2 with the topology of their own. But they contain many functions, including all holomorphic functions on a neighborhood of the closure. So they include all polynomials, they include most functions. Here I've given a reference for a recent reference for studying Dirichlet spaces. And I would also like to mention the de Bruijns-Rovniak spaces. This has its own theory, vast theory, which is really a topic of current research. These are basically images of certain operators on Hilbert spaces. These are subspaces, which are the images of Toeplitz operators defined as follows. What is a Toeplitz operator with symbol C in L infinity? It's basically a generalization of a multiplication operator. So you multiply C with F and then take the orthogonal projection onto H2. So these are generalizations of multiplication operators. So these are bounded operators, etc. So what is a de Bruijns-Rovniak space? Given B in the closed unit ball of H infinity, remember H infinity are bounded holomorphic functions on the unit disk. If it belongs to the closed unit ball, of course, it has the subprimum norm. So closed unit ball meaning subprimum less than equal to 1. Then the de Bruijns-Rovniak space H of B is the image of H2 under this operator, I minus TB adjunto, conjugate. This is a positive operator, so it has a positive square root. So these are basically the images of certain operators, certain positive operators within this space. And of course, there's a very vast literature, and I think these two volumes are a very good introduction to de Bruijns-Rovniak spaces. Okay, so finally, some more theory, because I can't state the results without talking about it. So the general theory of de Bruijns-Rovniak spaces divides into two distinct parts, whether the point B is an extreme point or a non-extreme point of the unit ball. So what is an extreme point of the unit ball? So an extreme point of any convex set is a point which doesn't lie on a line segment inside the space, basically. So for example, if you have a disk, every point is an extreme point, yes? So this is a fundamental difference between extreme points and non-extreme points. If B is an H2 in the unit ball, then the following are equivalent. If B is non-extreme point of the unit ball, then H of B contains all functions holomorphic in a neighborhood of D. Furthermore, if B is non-extreme, then there exists a unique function H with this a unique function A, which is called the Pythagorean pair, because it satisfies this property. It is a unique function which together with B satisfies this property, that A is modulus A square plus modulus B square is equal to 1 almost everywhere on the boundary. The star represents the boundary limits. Such a pair is called a Pythagorean pair, and the quotients belong to the Smirnov class. The Smirnov class are functions which are the quotients of bounded holomorphic functions, basically. Donald Saracen, unfortunately, he died a few years ago, several years ago. He passed away. He proved that, in fact, all Smirnov class functions arise as the quotients of a pair associated to non-extreme function. So this he proved quite recently. So why did I introduce all of this? In order to be able to study the unbounded inverse of I minus S. Because as I mentioned earlier, this is not invertible, but its inverse, its formal inverse is for an unbounded operator, it is very well behaved. Some things can be said about this operator. For example, the symbol 1 over 1 minus z is clearly a Smirnov class function because it is the quotient of two bounded holomorphic functions. So that means there must be a pair associated to this. So then there is a pair associated with phi, and in particular A, this of course I did not compute. This I fortunately just luckily found in this paper of Donald Saracen. He had computed it. But what's incredible about it is, and I don't consider this a coincidence, that the coefficient gamma that appears in this unique pair associated to this operator, which is of course essential for our approach to the Riemann hypothesis, is actually the golden ratio. So the golden ratio seems to appear there, which is very curious, of course, why the golden ratio somehow appears here. Therefore, so by a result in the paper of Constara and Ransfer from 2010, they actually proved that it's possible to calculate the domain of the adjoint of this unbounded operator. It turns out to be exactly the de Bruijns-Rovniak space at B. which is the pair associated to phi. And then they also proved that this de Brandes-Rovniak space is actually the local Dirichlet space at 1. So it's more easier to work with the local Dirichlet space than it is to work with the de Brandes-Rovniak space. So why is this interesting? Because using this fact, it is possible to prove the following result. Functions orthogonal to M. So remember, our goal was, as I mentioned, that we know that the Riemann hypothesis is equivalent to the orthogonal complement of n being trivial. Because remember, if the span of HK is dense, then the orthogonal complement must be trivial. So the idea is in this approach, we want to show that n perp is as small as possible. Of course, we would like to show it's trivial, but that's the Riemann hypothesis. So it turns out that using this theory of unbounded triplet operators in this context, we could show that n perp intersection with this local Dirichlet space is actually trivial. So what that means is, of course, not that n perp is trivial, but since this is a dense space, in fact, it is quite a large space, it doesn't intersect with n perp. That means n perp does not contain these functions. Of course, it could still contain an infinite dimensional subspace, but still, more recently this year, actually a few months ago, with my PhD students Juan's and Charles, we were able to, it's a preprint, we were able to actually prove a much vaster generalization of this result by proving that n perp doesn't intersect with any local Dirichlet space. So that means, in particular, no polynomials. So to explain what this really means, this basically, because remember, the local Dirichlet space functions are functions which behave well at the point zeta. So d delta zeta are all the holomorphic functions that in the Hardy space that behave well at the boundary point zeta. So when you say it doesn't intersect with any, it means that if there is a function in n perp, which would contradict the Riemann hypothesis, it must behave very exotically or very poorly at the boundary. In particular, we can say it contains no function holomorphic at even one point on the boundary. Because if you think of all holomorphic functions, even if they have singularities on the boundary, they usually have some points, like all elementary functions have some points on the boundary at which they are holomorphic, but this cannot be the case for n perp. So this, of course, we're just trying to deduce the consequences of this result, because obviously if there is a function there, that is if the Riemann hypothesis is false, then it must be a very complicated function in terms of its behavior on the boundary. So that's basically my presentation. Thank you very much.